is very important and key to any problem solving context. For example, you may have a Facebook profile, and you have a profile, you being represented as an individual in your Facebook. You may have a WhatsApp profile. You may have an educational institution profile. So, for example, IIITMK, one profile file also represents you. You may have a bank account. The bank will have your profile. You as an individual getting represent the context. Your representation in my classic case is your representation in m4marry.com will be different from your representation in IIITMK's file. Right, representation is always important in the problem solving context. So the first step in machine learning also is getting the right representation, and there is a theorem in machine learning called ugly duckling theorem. And what this theorem says is, so there is a group of ducklings, and one of these duckling do have a slightly deformed beak. All right, and your representation doesn't consider the beak at all. It represents wings color, wings, it represents the color, it represents certain other aspect of the duckling. It doesn't consider the beak at all. As long as the beak is not considered, the duckling, which is considered to be ugly primarily because the beak is slightly deformed, cannot be distinguished from the rest of the ducklings. So it is as beautiful as any other duckling because the aspect of it which represents it in the context doesn't capture the ugliness which is considered to be like kind of which is primarily the deformation in the beak. So ugly duckling theorem says there is no context independent representation for anything in any object. Right, there's only contextually relevant representation. So that's why you give enough data in your bank, you give enough data in your educational profile. So the first thing in any problem solving context is representing the objects of interest in the problem solving context. That's the first thing. And then, like, since it's a supervised learning paradigm, so somebody will tell these are apples, these are pears, these are dogs, cats, etc. And then you have training with the image or the object being represented properly with the training label. You undergo basically the algorithm is executed and training happens and you get a learned model. So given a new test case, what you do, right? You do the same set of features extracted, right? Using the learned model, you do a prediction, right? So it's very important that you have the right representation. Learn to predict the correct output is your problem, right? That's part of the thing. And I just want to give you, and I've not given you enough of examples, I thought I'll just run you through those examples. So learning from data, there are many, contexts where converting data to actionable knowledge is interesting. Actionable knowledge is nothing but intelligence, right? And that's what the algorithms do. Email spam filters doesn't need any explanation because, see, you have a smart, there is a machinery, there is a piece of algorithm which looks into spams and harms and then learns abstraction of a spam and at a personal level and a global level, and you get spam filters, right? Some algorithms use there are naive Bayes, rule mining, etc., etc. I don't want to get in there. We'll come to details later. Another example would be, I've already explained this, collaborative filtering. Amazon's recommender systems are built on collaborative filtering. Then there is nearest neighbor based recommender system. Recommender is basically, you may like this item also, we want to purchase this item also. He may be your friend, right? Such suggestions are recommender systems. Example for. Then comes learn to recognize faces and expressions. Doesn't need any explanation because you must have seen this in the social platforms where your face get tagged. Once there are public images, and the companies like Google do have kind of data with which you can even at a personal level can tag people, but it is, it's not legal in many contexts. Learn to identify vocal patterns. You want to distinguish whether this is this particular actor, or you want to distinguish between, say for example, Salman Khan and Amir Khan's voice, right? It's interesting. You can train machines out there. So learn to identify voice-based identity becoming very interesting these days. One fine day, like you may even feel that you can talk to talk to a speaker, a smart speaker, and speaker can identify you, give you access to a banking facility. It can happen. So for example, identity based on vocal patterns is an interesting part of research. AI based model building for your identity. All right. ML working with social data, detecting fraud, predicting click-through patterns, targeted advertising. Targeted advertising meaning you must have searched. You've received an email or you communicate with somebody on what do you call buying a new phone or whatever, and then you will see that your email is actually being what do you call the data platforms out there with the social platforms out there has already looked into your email and identified that you are you're interested in buying a new smartphone, and a lot of wherever you go, you're what do you call you are targeted with advertising on those contexts. You're considered to be an interesting, basically a mobile enthusiast, and then you get ads out there. So targeted advertising, click-through patterns, which all predicting click-through, like which will be the next thing that you will be interested in, you'll be clicking through, right? Detecting fraud in a context, detecting fraud in a login context, detecting fraud in an e-commerce context. Right, detecting. See, people used to do. Even today, you have means with which you can do what you call. There will be loopholes with which you can cheat e-commerce platforms and all that. The other way around also it happens. So you can actually like kind of fraud detection is an interesting AI problem. Character recognition doesn't need explanation. Identify what do you call. This is a D. Identify a Mandarin character, a printed character. So character recognition is interesting. From an image, can you detect a character? Document handling is very interesting. I told you about the legal example, right? You have a lot of documents. How do you convert these characters, this image into a textual form? And then what you can do is you can do mining around. You can do document mining, right? Legal example, say advocate gives keys in some query, and he should be able to retrieve what is relevant. Even from an image database, people are talking about it. And there are such systems, very successful systems in the Western market. Even in India, like when in Kerala, I've seen a few startups working on this. There are many solutions out there. Signature recognition, recognize your signature. That's it, as simple as that. Right, it's you. Biometrics doesn't need explanation, right? It can be iris-based or even your finger vein-based biometrics. People are talking about it. Or fingerprint based or finger vein based, right? Or even your what do you call handwriting based biometrics, right? Your voice based biometrics, aspect of your context would be captured. Fingerprint identification is an example for biometrics only. Object recognition, this is an animal, this is this is a switchboard, this is a cow, this is this is a football. So that's what it is. All right. Interpretation of aerial photography is an interesting image processing problem, right? So this is a grass field, this is forest, right? This area is empty, and there's a lot of vehicle movement here and all that. Autonomous autonomous cars are like, people are talking about not just land, underwater, space. And in an incubator that you are familiar with, Make a Village, we have an underwater, it's not completely autonomous, but there's an underwater drone out there, which can be used. There's a company which makes underwater drones in that Make a Village. So it's being supplied to Indian, forces and Indian governments and all that. So such autonomous things are beyond land. It can be underwater or space or whatever. Traffic monitoring, interesting, intelligence traffic monitoring, so that see whenever there is peak traffic on a particular line, you can actually do adaptive routing, which is which people are such systems do exist today. All right, you collect data, then you adjust your models. Basically, you take decisions based on the current context. All right, you have models to do that. Human activity recognition, this is a suspicious activity. Basically, this is a part of a larger problem called automated surveillance systems. Automated surveillance systems, from the video cameras and all that, you can detect posters, you can detect objects, you can select, there are people carrying harmful objects or whatever, and this being heavily leveraged in mission critical areas and highly secure areas. So this is, there are many such production systems in place today. Medical applications, you can detect from the imaging, you can detect. So basically you have systems which can assist radiologists and people of that kind, basically who detecting anomalies in body. Image annotation, right? You can say like, okay, there are four you can say like four fighter planes in the sky or whatever, and then jet is. So basically, like you have an image. Can you write a sentence about the image? right? That's the problem. So such systems are being built, and there are algorithms which does it today. Image retrieval, say, I mean, this is something that I think you must have already looked at. Your Amazon, you can click a picture, right? You can click a picture and then you can select, find me one similar to this. This is an example for a content-based image retrieval. It can even be a text-based image retrieval. The example that I've shown is text-based image retrieval. Show me the jet, right? So I should be able to, what do you call it, get the picture of a jet rather than, what do you call it, rather than a picture with an aircraft having propellers, right? So that's an example, text-based or content-based image retrievals. This is another thing that I've already gave you a feel of ECRM. ECRM is customer relations management. Say Lisa received one-to-one service as a store. How? Like so basically, like kind of, I mean, with all the interactions that Lisa had with the people. So marketing, I've seen interact with the web thing. So beyond a point, people collect a lot of data about you from different touch points that you have with a company or a business. And over time, they collect a lot of data. Now they know a lot about you. I mean, you must be knowing that your mobile phone or the companies which run software in your mobile phones runs more about you than you know about yourself. All right, it possibly knows like how many steps you have done today morning. It possibly knows what do you call, who are all people you frequently talk to. It possibly knows like who are all people you were pretty physically closer to. It probably knows like which all places you typically roam around. It may even know like whatever. I mean, if you have sensors enabled. Are you what do you call? Are you an animal which spends a lot of time outside or inside, or which all places your interests are? And the moment you add geographical data on top of the personal data that they collect on your mobile, they pretty much not know anything and everything about you. So basically, all I want is customer relationship management through data and building predictive. Supervised or what do you call unsupervised mechanisms or even reinforced mechanisms is a norm today. So ECRM platforms leverage a lot of it. Right, with that, so there are a lot of applications of machine learning and data intelligence around us. Let's get, I've already given you this. I thought I'll just give you the formal flavor also so that you can spend the week exploring this further. It's a definition of machine learning that I've taken from Mitchell, the book by Mitchell published in 1997. It's a program learns from experience. Experience is your data collected in that context, or data you get in that context, or data it's available with you. Experiencing with respect to some class of task. You are trying to learn to make aloo, whatever, right? Paneer butter masala. That's your problem. You're learning to drive a car, right? That's your problem context. So there's a task in front of you. A program learns from experience with respect to some class of task T and performance measure P. So for example, when do you say that you have learned to make a cup of tea? Somebody drinks your tea and says like, okay, hey, this looks tea. So this looks like a proper tea, right? Or a coffee. Or when your driving test you clear your driving test, somebody has, with respect to that performance criteria, you have learned to do it. And if the performance at task T measured by P improves our experience. So for example, you have a problem in hand and you learn to solve the problem, and you have a lot of data, contextual data, and as a learner, what you do is you try to solve the problem. All right, either you try to solve the problem from the available data and from the supervised learning, or what you call learned by doing it, reinforced, or completely unsupervised. Whatever be the mechanism, you try to solve your problem of the task in hand, and you try to build that abstraction or mental model or your knowledge in such a way that when you try next time with the new acquired skill or the knowledge, you should be able to do it better next time. And at some point in time, when you keep doing it, when you keep refining your knowledge or mental model, at some point in time, with respect to a performance criteria which is defined a priori, we'll talk about performance criteria later in the typical machine learning context. With respect to the performance criteria, somebody should qualify you as learned. You say that I know how to ride a car I drive a car because some, what you call, driving test has cleared me. That was my performance criteria, right? So we'll talk about it. So this is the formal definition of machine learning. And on the types of learning, which are classes of learning that you can do, right? I've give you examples. The typical classification, the image classification that you've seen in a supervised example, email classification slide that we have already seen. Then clustering, Amazon's recommender systems, or what do you call, collaborative filtering is an example for unsupervised learning. Reinforcement learning, your typical driving school, what do you call, instructor is reinforcement learning. Q learning is a typical is example. There comes the DeepMind. Right, supervised learning paradigm. How do you position your problem? You will have a training set. Say you call it Xi. So R, what do you call, in D-dimensional space. So Xi, you can imagine these are pictures of cats and pictures of dogs represented as a vector. I mean, in our case, we say like a D-dimensional vector. Y is a set of all categories. You have a two-class problem, cats and dogs. Right, you have data. And you have got M such. So in our case, we had 10 cats and 10 dogs. So we have got Xi, Yi, X1, X1 cat 1, X2 cat 2, X1 is cat, X3 cat 3, etc., up to 10. Then there are X11 is a dog picture. Then it says it's a dog 1, dog 2, etc. So we have two classes, dogs and cats. Set of categories is dogs and cats. And the images are your Xis. And you have got 20 of them in your earlier example. And my agenda is to learn to classify. This is a picture that I've taken from the famous book by Vladimir Vapnik, one of the pioneers in statistical learning theory. The book is called Nature of Statistical Learning Theory and Statistical Learning Theory, published in, I think, 95 and 96 or 98. 95 is the first book. So what it says is, yeah, so there is a generator and there is a learning algorithm. Generator is, for example, in your photograph, you can say like generator is a photographer, right? The person who takes a photograph. So you get a photograph X, and the supervisor says, hey, this is a dog. So Y, the corresponding label is there. So generator along with the supervisor creates a training set. What the learning algorithm uses is, it uses the data X along with the label Y, and then try to learn a function called f alpha of X. F alpha of X is given X, it give me an output f alpha of X. Alpha f is a set of class of functions. Alpha is a parameter. Say in the case of a neural network, the f is basically a particular neural network. Alpha is a set of all weights. What you learn is a weight. All right. Alpha is a tunable parameter of the model. In the case of, if your model is a tree structure, then the way in which the tree is built is basically the alpha. If your model is a probabilistic structure, the probability values you assign is alpha. How do you get alpha? You know, like, I'm going to learn a lot of probability values, and these are the probabilities that I need to learn. That's what the algorithm does. With the available data, with the training data, that the generated photo and the, what do you call, the label, the learning algorithm, what it does is, it basically assigns values. Hey, probability of a, let's assume that our training data is spam and ham emails. Some emails are ham and some emails are spam. All right, your model is a probabilistic model. Your model is a probabilistic model. Don't worry, we are going to build it. Right, when your model is a probabilistic model, and and certain probabilities needs to be found. When these words are available, what is the probability that this is a spam? So that's one probability value that you need to find. How do you find? From the training data, the algorithm has to figure out those values. And those values are actually the tunable parameters. So these values needs to be found is what the algorithm knows. And what are those values? How do you get those values? You get those values from the data. And that is alpha. The values are actually the parameterized form of the model is called alpha. So given a new X, the model learns f alpha of X. Model actually predicts f alpha of X once it has learned alpha from the available training data. All right. And when do you say the machine has learned? When Y and f alpha of X is given X, model predicts f alpha of X. If f alpha of X and Y are the same, you say like correct, otherwise it's wrong, right? So you keep your, what do you call, your training in such a way that you reduce the difference between Y and f alpha of X. This is typical. This is a classic diagram of the supervised learning paradigm. For example, problems I've already given you: optical character recognition. X is an image, Y is a character. Text classification. X is a document, Y is a category. Legal document or medical document. Spam detection, audit. Medical diagnosis. X is a set of features of a particular patient. age, sex, body type, blood type, ethnicity, etc., why indicates a risk. So this is an example for a classification task. This is a typical supervised learning paradigm. You need a lot of training data to say, train such models. Unsupervised learning paradigm, I've already given you the example for Amazon collaborative filtering. So this typically works by density estimations. For example, EM algorithm, you're going to see it. Clustering based approach. I've told you example of Amazon, where Amazon tries to cluster the users by using their by leveraging, utilizing their market basket data. The market basket of the same kind are grouped together. Examples for such algorithms would be K-means algorithm, which we are going to see, agglomerative algorithms, supported clustering. These are algorithms that we are going to see. So there is data, but there is no label. That's what it is. Right? Amazon's collaborative filtering is a typical example. The third category is reinforcement learning. It works like this. So there is an agent in an environment. Agent can actually do an action in an environment. So you apply your brake, right? That's an action, and the environment includes your your supervisor for your driving class and gives a feedback. It can be like based on whether the apply the brakes, vehicle stopped, the state is good. Hey, good, you stopped it, but you stopped in the middle of the road. Right, the state is not very good. Based on the state, the reward can be like different. So at any stage, you take an action. It's basically a sequence action pairs. So this is, I would say, it's a little more complicated than the supervised and unsupervised paradigm, and we don't have a lot of content on this kind of. Of course, we'll look at it, but we don't have any. I would say like I don't think we have content there in reinforcement learning paradigm in our course, but for those who are interested, we'll be pursuing a little. So this is basically an action, action reward based mechanism, where every action will have a state change, and from a state you take an action, and there'll be a reward or a penalty, and then the agent keep advancing in its position. So it goes like this. How to learn, behave successfully to achieve a goal while interacting with an external environment is the agenda. Game playing is a typical example. The player knows, right? And then immediately for every action, you have a feedback. Control systems, traffic control systems, right? See like traffic control system, it can take an action, then you see like certain roads are clogged. So the machine can actually learn to do it in a better fashion. You adjust parameters in such a way that that road will get a little more time. So what happens is like over time, the traffic system has to adapt its environment to its environment and can learn from its own actions. Penalty or reward. I mean, the traffic is smooth, so I don't have to do anything. So likewise, you can learn from every action. All right. RL model, each percept is enough to determine the state. The state can be read. From a game board, you can always read. The AlphaGo was made like this, and there'll be like ultimately your agenda is to find a sequence of state action pairs so that you get the best reward. That's called a strategy. I mean, those who have played chess and do have a game playing background, they'll know like there is something called strategy. Strategy is all about your long-term reward needs to be maximized, right? And for every action, you have a penalty, and you keep adjusting. So you based on your action state action pairs, you'll get feedback, or you keep improving yourself, or you keep adjusting yourself. And these are typically modeled. These systems are typically modeled as Markov decision processes, which I think your math course do have a little introduction to. And these are called MDPs. An MDP model would be typically like this, and don't worry too much about it. You'll have, for components, you'll have a set of states, actions that you can take as actions, and then there'll be a probability of transition from S to S dash given an action. So that's the conditional probability of getting to S dash by taking action A at state A, and there'll be an expected reward. All right, for every state action pair, there'll be an expected reward or penalty, penalization. So your agenda is like you start with S0, the initial state, and you keep taking actions. You move from state to state, and your task in reinforcement learning would be like we call it the strategy. We call it policy. We want to find a policy that maximizes the long-term measure of reward. That's what it is. And if you want to look at the reward action pair, you can you can aggregate it. Basically, like you have a probability at any state. Whenever you are at a particular state, you have a probability of taking an action right at that state, and so that you move to S dash, and then there is a reward from S to S dash using an action. So you evaluate all those probabilities, summed up, and you take that action which maximizes your what do you call notion of reward, your perceived notion of reward. And the best algorithm, known today is there's very little research has happened in this context, and one of the best celebrated algorithms out there is called Q-learning. I'll introduce you to Q-learning maybe towards the end of the course. And for the university, we just need this the basic introduction, but that's what it is. I thought I'll just share you. This slide is already put it in your classroom. You can download this slide. And that's all. That's pretty much about it. I thought I'll just finish this part because this is something that I've already discussed. And we'll continue. We'll start with supervised learning in the next class, and where we'll look at potentially maybe a neural network model, and then probably a probabilistic model, and then move on and we'll look at a hyperplane based model. So basically 3 classes of algorithms I'll introduce to supervised learning, and then maybe from different modules, and then we'll basically 3 class of algorithms in the supervised learning paradigm. These algorithms finds different types of abstraction. The models are different, so you get a feel of that, and then we go implement, and then we'll come back. So that's pretty much about the content today, and we'll have I want to share you a few action items and some interactions, and I'm stopping my recording out here. The recordings are available for you to pursue.